Hello, my name is Jonathan Moussa, and I'm a software scientist at the Molecular Sciences Software Institute at Virginia Tech. This short talk is my contribution to the 2020 virtual APS March meeting, as the physical meeting was canceled. The subject of this talk is the decomposition of quantum states inspired by standard matrix decompositions like the Cholesky decomposition, and for the purpose of better understanding quantum simulation. There's a lot of hype surrounding the use of noisy quantum hardware to simulate quantum systems, but there's also the countervailing possibility that noise makes quantum systems easier to simulate on classical computers. This talk briefly outlines a scenario in which noise very clearly enables efficient classical simulations of quantum systems. Now, I'm not a complexity theorist, and this isn't a complexity theory talk, but complexity theory is important to mention briefly for background and motivation. On the left, I've sketched out the standard Venn diagram of complexity classes that are relevant to quantum computing. Complexity theorists want to fit the combination of classical computers and unerror-corrected noisy quantum hardware somewhere into this landscape, but this is tricky. Such a device can efficiently compute anything in BPP, but not general problems in BQP, and there really aren't any well-defined complexity classes in between. Instead, they've focused on defining sampling problems, IQP sampling, boson sampling, random circuit sampling, etc., that accommodate noise by allowing the sample distribution to deviate slightly from the target distribution and can clearly prove the classical difficulty of classical simulation by showing that the underlying probability functions are sharp p-hard to classically evaluate. The classical cost of sampling these distributions is then guaranteed to be exponential in the number of quantum degrees of freedom, but it doesn't completely pin down the exponent of the cost. Also, the noise in quantum hardware becomes increasingly disruptive to sampling, and with hypothetical heralded errors, this would amount to an exponential decrease in the effective sampling rate. Thus, the pursuit of quantum supremacy, it's really a rat race between competing cost exponents. These exponents are very difficult to compare and come from very different technical considerations in practice. However, I've developed a theoretical model that allows them to be more directly compared, albeit under some very idealized circumstances. Here's a depiction of the noisy quantum circuit model that underlies this talk. This model was designed to use noise as a resource to reduce classical simulation costs. There are various properties of quantum systems that can keep these costs under control. For example, the bond dimension of matrix product states or the negativity of quasi-probability distributions. But here we keep costs under control simply by keeping the average size of quantum systems small. In this model, we alternate between preparing a qubit, operating on all the available qubits, and then applying an error channel to the new qubit. This error channel is a heralded measurement error, so when it occurs, it unambiguously reduces the size of the system that we have to simulate. Adjusting error rates controls both the classical simulation cost of this model and the effectiveness of sampling it from hypothetical noisy quantum hardware. High error rates make classical simulation easier because there are fewer qubits on average. If we want to sample a target cluster of qubits from hypothetical hardware, lower error rates reduce the number of times we have to run the circuit before the cluster of qubits survives against the noise. Somewhere in between these extremes is an error rate where these classical and quantum costs are equivalent. Now, it isn't obvious that these noisy circuits are useful for anything, especially since the noise is usually going to collapse most of the qubits. However, there are certain modes of operation that are useful, and one of them is depicted here. This circuit is a recursive decomposition of a general quantum state that has been known since the early 2000s. In general, the circuit depth is exponential in the number of qubits, so it's really a state preparation of last resort when we have no more clever way of preparing the state. For some states, these circuits can be very sparse, or we may be able to compress many of the controlled unitary gates in some clever way. I refer to this as universal quantum sampling because it has some basic parallels with universal quantum computation. Universal quantum computing can perform any unitary operation, but the generic circuit depth for doing so is also exponential in the number of qubits. It is the special cases where low-depth circuits are able to implement useful unitary operations, like Grover's algorithm and Shor's algorithm, that are so important. Universal quantum sampling is much less powerful than universal quantum computing, but it may still be quite useful for quantum simulation, since we could use these circuits in a variational quantum eigensolver, for example. The reason that these circuits are useful in the presence of heralded measurement errors is clear when we propagate such errors through the circuit. The errors commute with the controlled unitary gates and simply replace quantum controls with classical controls without spreading errors to the other qubits. The effect of these errors is to restrict the basis in which we can measure our variational state. It does not distort the underlying state itself. Also, we are always making high-weight measurements of the state since we always get to measure every qubit in the computational basis. However, only the handful of qubits that survive the noise can be measured outside of the computational basis. Thus, universal quantum sampling within this noise model is restricted in both the states that can be efficiently prepared and the observables that can be efficiently measured. Now I'm shifting the focus of this talk to a more mathematical description of the state decompositions inherent in the recursive quantum circuits that I just showed. First, I'll discuss an analogous scenario with classical states. On the top line, a classical state ρ is distributed over two subsystems labeled A and B, and we'll consider its decomposition into a state sigma that's only on the B subsystem and an operation R that extends sigma onto the A subsystem. We can invoke familiar concepts from probability theory in constructing all of these objects. Rho contains a joint probability over A and B, sigma contains the marginal probability on B, and the operation R is defined by the conditional probability of A conditioned on B. We can then imagine applying this decomposition recursively if A is one bit and B is all the previous bits, and we can continue by splitting off one bit from B to define a new A subsystem, and then applying this decomposition to sigma. If the conditional probabilities are efficiently computable, then we can efficiently sample this state and sample its entropy using the entropy chain rule. The pure state quantum case is not too much more complicated than the classical case. Now rho can be factored into a pure state psi AB, and sigma can be factored into a pure state psi B. Psi B looks somewhat like a quantum analog of a marginal state, but it's only defined up to an arbitrary phase. The operation R contains a quantum analog of a conditional state, again with some ambiguity inherited from the marginal state. The concept of a conditional quantum state is relatively uncommon, but not new. It was first discussed in the mid-1990s in the context of quantum Bayesian networks, and more recently put to use in variational Monte Carlo calculations based on deep autoregressive neural networks. It is when we move to the general mixed state quantum case that things get more complicated. Now the decomposition becomes highly non-unique. Here I'm showing an example decomposition where sigma is a pure phaseless state, but only the diagonal elements of sigma are actually uniquely prescribed by this decomposition. The operation R remains uniquely defined, but only up to the ambiguity in sigma. The form of R is heavily restricted compared with a general quantum operation, so that it's robust with respect to measurement errors on subsystem B. Again, when this decomposition is applied recursively, one qubit at a time, we can efficiently sample from a quantum state as long as most of the qubits are collapsed by measurement during the process. The entropy chain rule that was exact in the classical case now only provides us with a relatively loose bound on the von Neumann entropy of rho. While the simplest entropy bounds are loose, we can systematically tighten them. These bounds all come from the monotonicity of quantum relative entropy, and different bounds result from different choices of reference state sigma naught. The bounds become tighter as we increase the similarity between sigma naught and sigma, which, for example, can come from preserving the marginal state of sigma on increasingly large subsystems. While the resulting bounds become tighter, they also become more expensive to evaluate because they require brute force calculations of entropy on larger and larger subsystems. To facilitate efficient simulations, the R operations must be restricted to variational forms that are efficiently computable. On the left of the slide, I'm sketching out what this might look like for machine learning models. Generically, machine learning models are high-dimensional real or complex-valued functions with very flexible forms, but they don't typically build in application-specific constraints. In modeling the conditional probabilities or conditional quantum states, it's very straightforward to map from an unconstrained function f to functions satisfying the appropriate normalization and sign constraints. However, in the mixed state case at the bottom of the slide, the coefficient matrix for the R operation must be positive semi-definite, which is a matrix constraint rather than an element-wise constraint. It can be satisfied with a factored form, but this significantly complicates its evaluation and use in simulations. On the right of the slide, an alternative approach to modeling R is to first prepare the new subsystem in a trivial state, and then decompose the remaining action of R into a sequence of operations that each only act on a small qubit cluster. In the cartoon diagram, the operation preparing the green qubit in the bottom left corner might be decomposed into acting on a large cluster of qubits in its immediate vicinity, some mid-sized clusters far away, and then a periphery of many small clusters that are very far away and have a weak, diffuse influence on the state of the green qubit. To test out these state decompositions as practical simulation methods, I implemented them on some one-dimensional Ising models. Spins on the 1D lattice are prepared sequentially, and their preparation is conditioned on the state of n previous spins, where n is varied between 0 and 3 here. N equals 0 corresponds to mean field theory, so that instance can be calculated deterministically. N equals 1 turns out to be an exact solution for the classical Ising model, which makes the classical case rather uninteresting here. The quantum case with a transverse field of strength alpha is more interesting. I've plotted the energy per site relative to its approximation in second-order perturbation theory from either the low field or high field limits. These limits coincide at alpha equals 1, which is a quantum critical point. On this energy scale, the n equals 0 mean field solution doesn't look very good, but n equals 1 is sufficient for accurate results in the low field regime, and n equals 2 and n equals 3 show steady convergence in the high field regime. To scrutinize the performance at finite temperature, I set the field value to 1.15, which had the largest variational errors at 0 temperature. Again, the free energy per site is plotted relative to its approximation by second-order perturbation theory. The n equals 0 mean field result gets worse at intermediate temperatures, but errors steadily decrease with n, and they're reduced to a few tenths of a percent of the overall energy scale by the time we get to n equals 3. To conclude, the robust quantum state decompositions presented here have conceptual value in framing the pursuit of quantum supremacy and practical value as finite temperature variational Monte Carlo methods that could be very competitive with noisy quantum hardware for quantum simulation tasks in the future. A preprint of this work is available on the archive, the software used to generate my numerical results is available on GitHub, and I'm available via email to answer any questions. Finally, I'd like to thank the NSF for funding.